Is there any course with deadline today?
No, a week from today though, next Friday.
And the next Friday.
Yeah, no, but it means that you have some.
Yeah. Yeah, just everyone's working on this because next week you have geotechnics. Won't be able to do anything else.
Dissertations. So today I'm going to conclude on what we have done in a few recent sessions. And we just moved to the MDOF, stands for Multi-Degree of Freedom Systems. So far we discussed about single degree of freedom systems which had only a mass and a stiffness. And the partial differential equation was some sort of a very simple one with scalar values, mu double dots plus k equal to any external load you have. So mass m and stiffness k are apparently scalar values, they are numbers, right? But when we move to some sort of more complicated structures like building structures or any other sort of structures that have more than 1 degrees of freedom, we need to deal with some sort of more complex partial differential equation. I am on mute. Can you hear me, Sharif?
Yeah, I can hear you now. Thank you.
Thank you to letting me know. So I'm not mute and we are on record. Okay. So that's another thing. Anyway, if you want to deal with the stiffness matrix, we will come up with 18 by 18 stiffness matrix, a very big one. However, when we comply with the support conditions, we will eliminate 6 rows and 6 columns because we have 6 support reactions. And the remaining will be 18 minus 6, 12. Again, still, it's a very big matrix, isn't it? 12 by 12 matrix will be the stiffness matrix of this structure. But we will make some extra assumptions here, just to reduce that matrix to a very smaller one. But those assumptions are some sort of rational assumptions and just help us to simplify the example. However, you can do it with the 12 by 12 matrix, and that's okay. You can model it with 12 by 12, and you will see the results will be some sort of similar to this simplification. The simplification is, first of all, we assume that all of these vertical degrees of freedom systems are 0. The displacement along the all vertical degrees of freedoms are 0. I mean these 4. The displacement of deformation along this one, this one, this one, this one, and these are obviously 0 because of the support. But those 4 are 0 as well. Why I'm assuming this? Because the axial stiffness of the columns are very big. Because axial stiffness of the columns are very big. And if you really model this in ETABS and calculate those displacements for any sort of building, you will see that if your lateral displacement is something, this displacement is very small value in comparison with those displacement values. But this is a rational assumption to take into account here. So from those 18, actually 12, we are eliminating 4 of them. So we get down to 8 degrees of freedoms, right? Again, another assumption is, I assume that this is not 0, but I assume this is equal to this one. I only take 1 degrees of freedom system for both of them, because the lateral stiffness of the slab is too much, and the slab is rigid. And since the slab is rigid, the 2 sides of the slab deform identically. This is a good assumption. This is not wrong, because if you really model the slab here with a, I don't know, 20 centimeter concrete deck, you will see the deformations of the 2 sides of your slab are almost the same. So it is a good assumption to take these 2 as 1 degree of freedom system and these 2 as another. So with this assumption, we are decreasing 8 degrees of freedom system to 6, eliminating 2 more, right? So from 8, we get down to 6. And the last assumption is that I do not take the rotations into account. They are not 0, of course. They are not 0, but I just skip from them, because these 4, I just skip from these 4 deformations because they're not 0, obviously, but I can prove that if you skip from them, they do not contribute too much in the lateral deformation of your system. They are something, but if you want to calculate them, it's okay, you can go for them. But first of all, they do not contribute to the lateral deformations, these one, U2 and U1. They do not contribute too much to the U1 and U2. And also, when we want to design our columns, it's really about U1 and U2, and those rotations do not do too much in the design process. So with this later last assumption, we get down from 6 to 2 degrees of freedoms. And we can assume that in a very simple world, we can assume that this structure, which is originally has 18 degrees of freedom, has only 2 degrees of freedom, U1 and U2. Those lateral deformations in story number 1, story number 2. This is some sort of very big assumption, but getting down from 18 degrees of freedom to just only 2 degrees of freedom. But surprisingly, you can see that if you model your building in the ETABS with really 18 degrees of freedom, or really do it manually, it's a bit hassle, but you can do both. And you will see that the resulting U1 and U2 are almost the same when you just take 2 degrees of freedom, like U1 and U2. And these sort of assumptions are some sort of worthy stuff, because it enables us to simplify the problem as much as possible to be able to solve it manually and to better understand the behavior of the structure, dynamic behavior of the structure. So it is, although it is some simplification, but it helps us to better understand what is going on within the partial differential equation of the system. Any questions so far? Also, this subject is too wide. I'm just squeezing it into some specific frame, just to be able to wrap up this discussion along these limited sessions we have, considering we have lost some sessions out of my control. So I want to say that for a single degree of freedom system, if you remember, we had the partial differential equations like this: Cu dot plus Ku equal to Pt. Pt is external force, M is mass, C is damping, K is stiffness. U is deformation, U dot is velocity, and U double dot is acceleration. U dot and U double dot are some product of U, so they are correlated together. If you have U, you already have U dot and U double dot, right? Dot means the derivation against time, because we don't have X here in this problem of time. Everything is a function of time. So U is a function of time, so U dot and U double dot is time. So convention in this book is you don't use prime or something like that. We use dots because the emphasis of the derivation is against time, not X. So U is deformation, U dot and U double dot are products of deformation and velocity and acceleration. PT is any sort of external load.
What's G again?
Deformation.
Oh, deformation.
Deformation, like if it's vibrating like this, this is U, and this is U minus plus, this is positive, negative. All right? When we move from single degree of freedom system, this is single degree of freedom system, to multi-degree of freedom system, the form of partial differential equation is the same, stays the same. I'm not feeling like going through the demonstration, but the partial differential equation stays exactly the same, but everything goes from scalar to matrix and vector, or vector. What does it mean? It means that, for example, here we have a two-story building, right? For this two-story building, if it's three-story building, it will be 3 degrees of freedom. So also we have another assumption. We just concentrate on the buildings, not other complex structures. With some buildings like this. These M, C, and K are matrices. And the matrix dimension is exactly the same as the degree of freedom, number of degree of freedom in the structure. For example, here we have 2 by 2. It has 2 degrees of freedom, as we set assumptions. So the M matrix, C matrix, and K matrix is the 2 by 2 matrix, right? And U dot and U double dot are vectors, and PT. All of them are vectors. For example, U, here in this system, U is like this, a vector U1t, U2t. U1t is a scalar, U2t is a scalar, but they are a function of time. Like, you can assume that U1t works like a separate single degree of freedom system. U2t works as a separate single degree of freedom system. U1 and U2, every single of them are like this one, when it's a single degree of freedom system, right? But because we have a system with 2 degrees of freedom system, we have 2 kind of U1 and U2, right? And the K matrix is principally the same as what you have done in the matrix analysis. If you are really not in the dynamic mode, it means that you don't have velocity, you don't have acceleration, you have only Ku equal to P. It's static, it's what we had in matrix analysis, right? That's why the K is exactly the same as what we had in the matrix analysis. But we have C and M, something that we need to deal with. C is some sort of damping, representing damping, and M is mass matrix, representing the mass. The mass matrix for building structures like this one can be demonstrated that it's simply written here. The mass matrix maybe it's better to work here. This is the partial differential equation system for a multi-degree of freedom system. And for a simple one, 2-story building, the mass is M1, M2, 0, 0. M1 is the whole mass in the first story, M2 is the whole mass in the second story. If you have a 5-story building, it's M1, M2, M3, M4, M5, 5 by 5. Right? The K is K1 plus K2 minus K2 minus K2 plus K2. K1 is the summation of stiffnesses of all the columns in the first story What does it mean, the stiffness? Stiffness means, for example, you have two columns here. This is first story, this is second story. The stiffness for this story is 2 times of, because I have 2 columns. Each column's stiffness is 12 EI over L3 cubic L. We had this. If this slab is rigid, it's 12 EI over L3. For this, whatever column we have. For the second column, this is K1. K2 is again 2 times 12 EI over L3 for these 2 columns. If they are different, you need to take into account different characteristics of different columns, right? And if you have 3 degrees of freedom system, just like I write here, for a 3 degree of freedom system, the stiffness will be like this: K1 plus K2, K2 plus K3, plus K3, minus K2, minus K2, minus K3, minus K3, sorry, no, 0 here, 0 here, minus K3, minus K3. It has a pattern, you know, K1 plus K2, K2 plus K3, K3 plus K4. The last one is the last K for the roof. And you need to put some minus K2, minus K3, minus K4, minus K5 in this band of your matrix. The rest are 0. Right? If you have n story, it's very easy to write this stiffness matrix. The principal diagonal line is like K1 plus K2, K2 plus K3, K3 plus K4. Except the last one, which is K roof. Here is K3. This is the K3. You need another band here, another band here. The rest are 0. Right? This is the mass matrix. This is the stiffness matrix. The damping matrix is very difficult to calculate. The damping matrix, damping is a very complex phenomenon. Damping is a very complex phenomenon. Calculation of C is very complex, really. If you want to be precise, you need to go to the laboratory, do some very complex experiments for your stuff, like if you have concrete wall or concrete element, steel element, to see how much the damping is. However, there is another very big assumption to simplify this problem, and that's like because first of all, although damping is very complex, but because this is some sort of very small in comparison with the other 2 terms, mu double dot and Ku. If you remember, the damping ratio was 5%, 2%, 3%. So the whole term of Cu dot is a very small value in comparison with mu double dot and Ku, generally. It means that maybe I can say the second term, Cu dot, is not a big deal when we compare them to, when we compare it with the 2 adjacent terms. So it's probably not a big deal if I assume some sort of simplification with this middle term. And usually the simplification is that we assume that this C matrix is a combination of mass and stiffness matrix. A fraction of mass plus another fraction of stiffness makes C matrix. This is a very big assumption, but it still works in most of the cases. And don't worry about this, because sometimes we ideally assume we don't have damping. Damping is 0. Just solve the problem, although it's not realistic. In any case, we have some damping in place. But don't worry about the damping. We mostly deal with mass and stiffness. So, if you have the mass matrix and the stiffness matrix for your system, as you do, the next step is to solve the, this is not still anymore the partial differential equation. It's a system of partial differential equation. Because you have really, it's like if I rewrite everything we had, so far, it's like this one. Whereas 2 by 2, two-story building, N1, 0, 0, and 2. U double dot 1, U double dot 2, plus, forget about damping. Damping is not important too much. K1 plus K2 minus K2 minus K2, K2, U1, U2. And you can assume we have P1T and P2T, or you can assume 0 and 0. It's a free vibration, like I get it and release it, it will vibrate. Anyway, this is the system of partial differential equations for two-story building. Why I call it system? Because it's not only one, it's two. If you have 10-story building, it will be 10. You can just figure your matrices, right? And can I write it like this? I can bring it out from the matrix form by multiplying this line by this line will be M1 U double dot 1 plus this line by this line is K1 plus K2 U1 minus K2 U2 equal to P1T. The second line is this line multiplied by this line, M2. I'm just multiplying the matrices to the vectors. M2 U double dot 2 plus or minus K2 U1 plus K2 U2 equal to P2T. It's a system of two equations. Do you remember you had a system of equations like two equations and two unknowns, x and y? You had quite a few number of methods to solve those kind of systems. We had them already in the matrix analysis, didn't we? We used to inverse the matrix, multiply, or you can use some other conventional methods you already knew from high school, probably, right? This is exactly the same somehow, but there are two different things. First of all, this system of equation does not deal only with U1 and U2. It deals with the derivation of them as well. We have double dot and possibly dot. I just assume that we don't have damping, but if I assume that we have damping, we have some terms of U dot 1 or U dot 2. Anyway, we have U double dot 1 and U double dot 2. So it means that it's like those systems of equations like x and y, but we have x dot and y dot as well. It's more complex, isn't it? And the second problem is they are not independent, the first one and the second equation. The first equation deals with U1 and the derivation of U1, okay, but still you have U2. They are interconnected together. It makes physical sense because it means that if you have a two-story building, story 2, story 1, if I hold the story 2 and release it, the story 1 will also vibrate. That doesn't stay there still, right? if I get the story 1 and pull it and release it, both stories will vibrate because they are connected together. The first story connects to some columns at the bottom and some columns at the top, and if you put an initial condition, or if you put any external forces to any of them, both will vibrate. So it means that in mathematical form, it means that these two equations are interconnected together. The second one deals with U2, but again, we have U1 here. So in each of them, we have both unknowns together, U1, U2, and the derivations of them, right? It makes it very difficult to solve it with conventional methods. So it's probably the most difficult partial differential equation sort of solving in physical terms for structural engineering. That, again, you need to assume some simplifications, otherwise it's extremely difficult or maybe impossible to solve these equations. The first assumption is for damping. I said that. The second assumption is helps to solve these equations. And this assumption comes from a concept in applied mathematics, which is called, I don't know, maybe you have seen it somewhere in some other modules. It's called separation of variables. Have you ever heard separation of variables or not? So it's a concept that helps you to solve some of the partial differential equations, especially when they are in the form of a system of equations. And before I go to that, just take a look here. It's better represented here. For this two-story building, we have this mass at the second story and this mass at the first story. And this means that the slab is rigid. Slab is something like, I don't know, 20 centimeter thick concrete slab, which means we have rigid slab here. The assumption is valid that this horizontal deformation is identical to this one, that both sides of this slab deform the same. And this is the system of partial differential equations. This is the mass stiffness. This is the mass matrix. This is the stiffness matrix. This is the vector of accelerations. This is the vector of deformations, and this is the vector of external forces. And we are neglecting the damping in this form. And as you see, the interconnection between these two equations are coming from these two terms, aren't they? Because when I multiplied in the previous slide, when I multiplied these two equations together, this is the responsible term that brings minus 1 U2 in the first equation, and this is the responsible term that brings the minus U2 in the second equation. Otherwise, if, I would say in this form, put it in this way, if, it's not like this, but if you had 0 here and here, the two equations were separated. We didn't have any U2 in the first form, and we didn't have any U1 in the second. And if those two equations are separated, you can simply solve them. because they are absolutely like single degree of freedom system that we have some Excel files to solve them, right? We already know how to solve single degree of freedom system. All of the Excel files from last sessions are talking about solving single degree of freedom systems. So to be able to solve this problem, you need to assume an extra assumption which comes from separation of variables. And that assumption is some sort of, we can assume U1 and U2, which is the final unknown, the vector of U, is the summation of I just want to be consistent with the book notation. What is the book notation? Phi and Q and T, okay. Just to be consistent with the book notation. N is the degrees of freedoms you have. Here, N is 2, right? And it means that, I continue it here, it means that I'm assuming phi1 q1t plus phi2 q2t. It's named separation of variables because we are some sort of assuming the solution of this system of equation is a product of two things, phi and q. Phi is only a function of geometry, not time, and q is a function of time. Because we know that the u, the final product we are looking for, the unknown of this problem, is a function of location and time. Because what does a location mean? Location means either in story 1 or story 2, right? So the formation of the system, U1 and U2, is really a function of location. Where is it? Story 1 or story 2? And what time is it? It's a function of time as well. That's why we're assuming it's a combination of phi as a function of location and q as a function of time. It's really an assumption, but in applied mathematics, for some of the partial differential equations, if the problem is, this is an assumption, but if you do not take this assumption, there might not be any sort of method to solve the partial differential equation, really. And that's why this is a well-known method to solve some of the partial differential equations in the applied mathematics. Otherwise, somebody can say, okay, maybe this is a restriction to the problem environment, and there might be some other solutions. The answer is yes, there might be some other solutions, but we don't know how to solve this equation if I don't take this assumption, which comes from separation of variables. So the story short is that if we assume this assumption, if we accept this assumption, the whole system of equation will be simplified into here 2, but if you have 10 story buildings in 10 single degree of freedom systems, which I know how to solve them. The advantage of this assumption is breaks down the whole complex system into smaller pieces of system. Each represents exactly like the single degree of freedom system. And this term comes from the single degree of freedom system. So, for example, here, this is like a single degree of freedom system. This is like another single degree of freedom system. this is like T1, this is like T2. That's why I was telling you in the past sessions that for the multi-degree of freedom system, we have a set of natural frequencies, not one. That's why for a two-story building, we have two natural frequencies, T1 and T2. For a 10-story building, we have 10 natural frequencies, T1, T2, T3, T4 to Tn. And another important point is that if you really solve this problem, and find your ut, final unknown u, you will see that 90% or 95% of this u relies in the first term. More than 90% of the u information relies in the first term, not in the second term. And if you have a 10-story building, it's really like this. We have 10 terms, Phi1, Q1, Phi2, Q2, go ahead to Phi10, Q10. And in the 10-story building, if you really solve the problem, you will see that what you will get for u unknown, which is u, 90% relies to Phi1, Q1. I don't know, 5% relies into the second term. Less than 1% relies to the third, fourth, fifth. Go ahead. So the first term is dominant. The first term is the most important term to solve this problem. That's why it's called the first natural frequency is the dominant frequency. It's the most important frequency. And again, that's why we there are some simplified methods in the Eurocode and other codes as well. Just by taking the first term into account and simplify everything. I mean, neglect the second term, etc. Just take the first term into account, right? And the problem is that the next step is, the problem, we're not going to completely solve this. I just wanted to give you an idea how does it work. But the next step is how we can find these T1 and T2, the natural frequencies of our system, right? For this purpose, you need to go for some sort of analysis, which is called eigenvalue analysis. Eigenvalue analysis helps you to overcome with this problem, that what are the natural frequencies of the system, T1, T2, T3. These T1, T2, T3, T4 are natural frequencies of system, or better say natural periods of the system. Because when we talk about T, it's natural period. If we bring it to F, 1 over T, it's frequency. If we bring it to omega, it's radian over second. So, but civil engineers usually feel like working with T. Most likely, mechanical engineers like to work with hertz, with frequency. But when I say natural frequency, I really mean T1, T2, T3. I mean natural period. They are all the same thing, but in different form of presentation. Your coursework is about to calculate T1, T2, T3, T4 for building structure. If you take a look at that, the coursework is about really how to calculate T1, T2, T3. right? Because principally, with those Excel files, you know how to calculate Q1, Q2, etc. And the only thing you don't know is how to calculate the natural frequencies. T1, T2 are called natural periods, and phi1, phi2 are, or better saying, T1, T2 are eigenvalues, natural periods, because they are coming from a sort of analysis which is called eigenvalue analysis. They are eigenvalues. It's a name of the analysis. You will see how does it work. Okay. And phi1 and phi2 are called eigenvectors. T1 and T2 are eigenvalues, and phi1 and phi2 are eigenvectors. And the coursework is about how to calculate T1, T2, T3, etc., and phi1, phi2, phi3, etc. For the coursework, but I just want to leave this discussion, hold this discussion here, because I will go through how to calculate eigenvalues, eigenvectors, T1, T2, T3, phi1, phi2, phi3. Once with ETABS, once with MATLAB or Excel, we can use any of them to calculate eigenvalue analysis. Okay, but I just wanted to give you an idea what the problem is. I will leave this discussion for the 2 weeks, the last session we have at the end of April, how to calculate the whole process of eigenvalue analysis with ETABS, MATLAB, Excel, etc. And for now, I want to emphasize that here, this part, sorry. This part goes to Eurocode 8 by assuming that the other terms are not important. The first term is important, only T1, only phi1, Q1. And this terms means that the whole complex system can be simplified by a single degree of freedom system with a natural period of T1. For the single degree of freedom system, you have Excel sheets, you can calculate whatever you want, right? But with this assumption, this part, this solution goes to Eurocode for seismic loading of the structures. Here we have two things to do. First of all is the eigenvalue analysis. I just hold it, leave it for the next 2 sessions to deal properly with that problem for your coursework. Okay, we will do a lot of stuff for the eigenvalue analysis. Okay, after you finish your dissertation, just to have free space in your mind to deal with the eigenvalue problem. Today, after a short break, we will go through the implementation of this term into the Eurocode 8, about a couple of slides left from last week, remember, right? So we'll have a short break, please. Let's come back in 5 past, almost 10 minutes. And then we will deal with those slides, how the Eurocode 8 deals with this problem for seismic loading of the structures, right? Just grab some air, stretch your leg if you want, and we'll resume at 5 past.
You get.
Good morning. I saw your email. Unfortunately not. After this class, I set a meeting with the students for the reset third attempt of master students. Third attempt, it has something. And I need to see what they are doing, you know. But I will think of when we can do that, okay? After that, I need to catch my phone.
Right, what about you? Yeah, I'm back for a day, bro.
Yeah, like that.
How far did you get?
I'm on
I will
methodology.
do my best to do it on Monday. If you are available. Okay, bring it out. Or maybe, are you here after finishing the class? We can probably have something like that before I start the next session.
Yeah.
Are you able to stay?
Yeah, after the class. That's fine.
No, it's okay. Let's do it after this class, okay? Because my session will start at 11:30.
So no methodology.
More or less, I should have.
Should be that long. Let's follow what I've done in the experiment. Possible. I'll supervise.
It's right.
This is what that's the work I'm doing.
Did you do the example though?
Or do that around. I was doing, I came on Wednesday. I was doing on Wednesday.
So I'll say just finished probably.
Probably waking up at fucking 9 all day, bro. I'm waking up at like 11.
I didn't use
That's what you did. I got my phone. You get off.
It doesn't say 500. I'm gonna do that today though, so. All the analysis.
It's here.
I don't know.
How you on it? GPT. I'm gonna load up chat GPT.
My thinking is 42% similarity.
Hi.
Huh?
Hi.
It's quite the reason why is because the formatting, everyone's using the same format. So it's 19%.
Did you reword it?
It's fine, like most of it was just because of the formatting. It was like everyone was submitted.
No, you know the chat GPT, did you copy and paste from that?
I rewrote it. Sometimes I told ChatGPT to reword it, but make it sound less like AI.
Finish having conversations with it.
Bro, proper talking. Ask it everything.
Long time I solved my code on that. Fantastic. Oh, very great to help.
That should do the book.
Bro,
And then put the correct.
which one is it? I think.
Oh my days.
Hit the mod. I'll put my code in. Wasn't your show with it, then modifies it. Piss.
I should pick that up in the situation.
And then I can tell you use my methodology in it. If you don't say my methodology, I'll give you another script. Again, doctorate script. After using my methodology, with minimal changes can be modified in code. Use the exact same code as me, just add a few things.
You want to submit that?
Yeah. Then, what the? Ask ChatGPT.
Huh?
Ask Chat. Probably ask you about that.
Yeah, man. I forgot. So for
Is
you,
it long, that concrete? Is it as long as concrete? As long as I don't.
it doesn't and calculations. And then you just run it on Praxis. So Praxis is at the end.
Then I compare.
Then yeah, just analyze the results of Praxis.
So if you want to prop on that report though.
It's got a thing. Problem definition, problem analysis. It's kind of long. But it's long.
And then I'll start today.
Can't eat dissertation.
Shall we continue?
The family will wake up early and dissertation.
So, this is the remaining slides from last week. And exactly coming from Eurocode 8.
That's our next
This
week.
part is really
Wait for Panos to put the tutorials in there.
seismic loading structures.
Well, have you done the calculation?
It deals with this problem that you already have had some sort of modules dealing with gravity loads like dead load, wild load, imposed load, and the only natural load you had is wind load, isn't it? So wind load is lateral load, but really different from seismic load because wind load is really depends on the wind speed, which is out of your control, and also the area of your structure facing the wind. So it doesn't really meet the mass of your structure, does it? But seismic load is really kind of load. If you take a look at those Excel sheet we practiced in previous lectures, it really deals with the mass and the stiffness of your structure. So it really doesn't depend on any sort of area facing anything, etc. It really matters how much weight your structure has and how much stiffness your structure has. The Eurocode's formula, this one, for seismic loading of structure is very straightforward. To prove this formula, it's very straightforward. It's here. FB is the loading on your structure. FB is the seismic load on your structure, which is horizontal. It means that if you have this sort of two-story building, the summation of these two forces are FB. I will distribute FB in some sense between two forces in different stories. That's another problem, okay? But you can call it FB2 and FB1. FB is FB2 plus FB1, the total FB, which is called the base force. Because, well, why that's called the base force? Because if you cut the structure here, the equilibrium equation says FB should be equal to FB1 plus FB2. If you cut your structure above the foundation, the full force diagram of your system is FB and FB1, FB2. When you comply with the correlative equation as summation F against x-axis should be 0, right? So FB is the seismic loading, and this is the Newton law, isn't it? The Newton law says when you have acceleration, the force is the multiplication of acceleration by mass, right? This is the Newton law. This is the case for single degree of freedom systems. The Eurocode says I use a correction factor as lambda because I'm using only that first term, E1, Q1, before the break, right? The first term, the natural frequency corresponding to the first natural period. And because that first is some sort of 90% of the total thing, this is a correction factor just to take that effect into account. So I'm not dealing with the total mass, I'm dealing with some sort of a fraction of mass. Lambda either is 0.85 or 1. So not a big deal, don't worry about it. And the acceleration is reduced here by a factor of q because of some other reasons. I'll tell you why. And the whole acceleration divided by q named as dq, as SQ, sorry, SQ, SD T1. Why it said T1? Because I'm dealing only with that first term about the first natural frequency of the structure. T1 is the first natural period of the structure. So this term depends on the natural frequency of this structure, first natural frequency of the structure. So this is mass, easy to find. And you remember when we deal with the Excel sheet, I said we rather work with mass than stiffness, because stiffness is tricky to deal with. But that's why we use spectral acceleration instead of spectral displacement in those Excel sheets, right? That's why here we are using spectral acceleration as well. This is exactly a spectral acceleration in the Excel file last week. SA is exactly a spectral acceleration in the Excel file, but in the Eurocode, it has provided a ready-to-be-used spectral acceleration for the engineers, right? This is exactly, SA is exactly the spectral acceleration we used last week. We prepared it in the Excel. We used it for 4 simple examples we solved. Do you remember? We had a central spectral acceleration. We had a very simple one-story building. We solved it for this central spectral acceleration. This SA is exactly that one. And the only difference is last week we deal with a spectral acceleration corresponding to the L central earthquake. Today, Eurocode says I will give you a ready-to-use spectral acceleration, not for L central, for any kind of earthquake will happen in your region. But I want to take some other factors into account, for example, soil type, which is very important. Because El Centro has happened in America, but if it happens in Italy, what will happen? If it happens in Italy, one place is a firm soil, one place is a soft soil. What is the difference? So we need to take the soil effect into account into this spectral acceleration as well. That's why the Eurocode 8 has prepared some prescription for designers to put some effort to consider the soil type and also some other factors inside this spectral acceleration term in the formula. The only point is, what is Q? Q Q is behavior factor. It's called behavior factor. And it's always more than one. It's 2, 3, 4, 5, something like this. And the behavior factor aims to reduce your forces, as you see, because it's in the denominator. And it reduces your seismic loads, doesn't it? The reason is the Q factor stands for the fact that the structure is able to go beyond the yielding point and go to the nonlinear range of behavior and get some damages just to be able, not collapse, just to get some damages, but will be able to use its capabilities in the nonlinear behavior just for the reason, I don't want to be so conservative in my design. I want to use the nonlinear behavior of the structure. Otherwise, if you don't use it, your design will be so conservative and non-optimized, and you need to put too much money there. So if you set Q equal to 1, it means that your structure will behave elastically during the earthquake and does not go into the nonlinear behavior, which is possible, but not optimized, it's too conservative somehow. You're not using the nonlinear capabilities and capacities of your structure. So, I want to give you an example based on the Eurocode how we can use this formula. Okay, very simple one. It's just using some tables and formulas. Like there is a table 5.1 as you see, and we are going to solve a problem. We have some assumptions for definition for our problem. I've listed them here. I'm talking about a multi-story steel frame building. The equivalent static analysis is eligible. Equivalent static analysis is the name of sort of analysis which takes only that first term into account, P1, Q1. It works only based on the first natural frequency of the structure. DCH ductility class. Ductility class is high. Ductility class is high, is related to the Q factor. That Q factor which is about the nonlinear capability of the structure. You have table 5.1. If you have ductility class high or ductility class medium or high. Okay, I will use this column. And this is my structure is a frame system, wall system, coupled wall system. Mine is frame system because it's a multi-story steel structure. So I will calculate Q0. This helps me to get Q0 as 4.5 alpha U over alpha 1. And as you see, I come here for a multi-story building. The ratio of alpha U over alpha 1 is 1.3. And it means that Q, this is, doesn't work very well there. This is Q, a behavior factor. Behavior factor, which is 4.5 coming from this table. This ratio is 1.3. I will get 5.85 behavior factor. This is the factor I will put here, just to reduce the spectral acceleration. Okay? Two things are very important. These two. 1, 2. These two will go into the spectral acceleration calculation. One is soil type. Soil type is C. You will see we have some sort of A, B, C, D. I will show you. And it stands for the fact that it should be different if we are designing in Italy or wherever it is. In one city, my building is going to construct it on a firm soil. In another city, is going to construct it in a soft soil. It should be some difference. There should be some difference, right? the soil type should be some parameter into our calculation. And the ground acceleration on stiff soil is 0.35. It means that the area, the location should be important, because it should be different if you're designing a building in the United Kingdom, or in Italy, or in Greece, or in Romania. The level of seismicity, level of potential earthquakes is different in different regions, in different locations, right? That's why this is represented by the ground acceleration, means the potential possible acceleration in the ground in that site that you're going to construct your structure is 0.35 G. Okay? This is dimensionless. I mean, if you put G 9.81, you will get meter per square second. So the next step is the Eurocode gives you some very simple formula for calculating your T1. You are going to calculate T1 based on your coursework, and you can use this to see how the difference is your calculation with this one. This is more conservative than you will calculate in your coursework, because any code, including Eurocode, wants to be conservative. They aim to be conservative. So the thing that the T1 you will calculate in your coursework will be definitely more than this one. More than this one you will get from the Eurocode. Okay, from the Eurocode, this is coming from the Eurocode. If you have buildings up to 40 meter, T1 can be calculated by this, and C1 is equal to 0.085 for the moment resisting frames, and it's my case as well. This is the height of my structure. I will get this one as T1, 1.035 second. Okay? You will calculate this one based on your coursework. You will come up with T2, T3, T4 as well. It's good to compare your T1 from the coursework with this formula to see how the difference is, but in advance I can assure you your calculation will be larger than the T1 provided by the Eurocode. And these are 4 formulas. I showed you this last week, if you remember. These are 4 formulas which help you to come up with your spectral acceleration. These 4 formulas provide you with SAT1. We figured out how to calculate Q based on those tables. This SAT1, which is a function of T1, we already have T1. This SAT1 comes from here. And there is a table, as you see here. This takes into account the soil type. We have ground type A, B, C, D, E. There is another table which shows what does it mean, A, B, C, D. I don't have it here. It's in the Eurocode. It really depends on the laboratory tests you do on your soils. You perform a boreholing test and grab some data and then figure out what type of soil you have. So you will be either A is the best, going to E is getting worse. So A is the most firm soil. For this example, I'm assuming I'm C type for the soil. I will get 4 parameters here for my soil type, as listed here. If I have these parameters, I can put them into these formulas and simply come up with I'll put all of these formulas into the Excel. Not this one. I showed you last week this figure, don't you remember? T and ST. 1, 2, 3, 4. 4 parts, 4 formulas. These 4 formulas, if you put these variables inside them, you will get absolutely this figure, right? So it's very easy to go to the x-axis, which is t. You already have your t1, right? You have t1. We calculated already t1, 1.035 seconds. With this t1, we go to the Excel file. With these 4 parts, I just plot the shape of the spectral acceleration. You just go here, 1.035, and read this number. You only need to read one number from whole the graph. And this goes to your formula. You don't need the whole picture, the whole plot. I just plotted into Excel just to see what does it look like. But you only need one point of the data. So if you put you see a bump here because I put this number here just to have the exact number for my case. Otherwise, I usually go 0.1 increment in this region. Otherwise, I just get this data from this point and bring it here. So I'm using this value, which is absolutely coming from here. This is absolutely this one. And this is the spectral acceleration you should put in your formula. So here we are. The total mass I have in my building is this one. The seismic load is the total mass multiplied by a spectral acceleration I got from there. This G is just for because the spectral acceleration is in terms of G, the percent of G. G should be added here, and lambda is 0.85. If I put G in terms of inch over square second, in this case, or if you're working with SI units, you can put it 9.81 meter over square second. I will get 112,000 pounds as the seismic load on the structure. It means that this is not true story building, whatever it is, you should put some FB, FB1, FB2, go to FBN. This is FB. FB is summation of all FBI. I goes from 1 to n. All of these are in agreement with the FB, and the FB is this one. There is a very simple formula in the Eurocode to dispense the FB into the FB 1, 2, 3, 4, 5, 6. It's based on the proportional to the mass to each story. It's not a big deal. So the FB is important, the base factor, the base force. And as a rule of thumb, I introduce you as a new parameter here, or seismic coefficient. If you remember, FB was lambda M SA T1 over Q. This is the Eurocode formula, wasn't it? Right? If you keep M here, okay, and like this, lambda SA T1 over Q, everything but M. Okay? We put everything in one bracket and M in out of the bracket. It means that this one is, in this case, is 0.84. It means that it's 8% of the mass. The seismic load is 8% of the mass. This is a rule of thumb because it's usually between 5 and 12%, just to control if you are in the range or not. It should be something like 5%, 10%, 12%, sometimes maybe 15%. It doesn't go beyond 15% of the total mass. In this case, it's 8.4%. Why I'm introducing you this new parameter, because there is a science history behind it. The seismic loading on the structure, the whole structural knowledge we have about it, goes back into probably 100 years ago at max. But the structural analysis goes to a couple of 100 years back. For example, we didn't discuss this in this module, but yeah, these methods, the stiffness methods, stuff like that, they are Euler method, the buckling formulas. The buckling formula goes back to 1544. So it means almost 300 years ago. Okay? Structure engineering formulas, buckling and structural analysis, etc. Some of them go back to 300 years ago. But seismic loading, seismic design really goes back to less than 100 years ago. So they are younger than structural analysis. And why I say that, in 19th century, like 1910, 20, something like that, in the seismic prone areas, the people see that during earthquake, different earthquakes, buildings collapse. And they didn't know why. There was not any knowledge like this at that time. And they didn't know why this happens, but they did know that some sort of lateral collapse occurs because building is going to destroy in some sort of vibration in lateral deformation and collapses, right? They intuitively felt that there should be some lateral push to the structure. They didn't know these theories at all. In 1920-30, for the first time in the United States and some parts of the Europe, no, probably only in the United States and then in the Europe, they mandated the engineers to consider a fraction of weight of the structure as a horizontal load to the structure design. And in that time, they didn't know how much. They didn't have any background, any scientific background in that time. None of these theories were developed in that time. But from their engineering judgments, they proposed to use something like 10% or 12% of the weight of the total weight of the structure as a horizontal load to the structure. And this 10% was correct, although there was not any background for it. It was just feeling. It was just, engineering judgment. And then these theories started to be developed in 1950, 60, a couple of decades after that. And the whole figure was more clear. And now it's clear that in that time, those engineers were brilliant, bright minds, that proposed to have some sort of 10% of the weight of structure as a horizontal load of design.
What's left, trial and error?
Not trial and error. They didn't have any code like this. They just started for the first time in history. They just mandates the designers in these earthquake-prone areas, because before that they just designed the structures for the gravity loads, only for the gravity loads. For the first time, they said, okay, in addition to the gravity load, we should put a horizontal force for the structures equal to 10% of or 12% of the weight, in addition to the gravity. And it was the rule of practice in some of the states in the United States for the first time. After that, okay, the science were developed these theories, and nowadays we know that that was a wise decision at that time. And you see now in the Eurocode, for this example, you get 8% of the weight. It does make sense. My point is, in that time, without any of these, they had a good judgment. They roughly said 10% of the weight, 12% of the weight, and it was a correct decision. And that's why you can find similar stories in the engineering history that brings you to the point that although we deal with so many numbers, so many theories, so many partial differential equations, methods, numericals, finite elements, but at the end, you will believe that engineering, structural engineering is more art than science. If you just dive into the numbers without knowing what they mean really, you may really go to some dark places without any feeling if your structure is really perform good or not. Right? I probably provided you with an example for a cathedral in Spain in term 1. Was it this class or?
I can't paste it, I'm not allowed to paste it.
Do you remember anything? So it was not here. There is a cathedral in Barcelona or Madrid. It's like a tree. If you look at the picture, it's a very big cathedral, very beautiful one. It's still under repair, and the construction goes back to a couple of 100 years ago, probably. It's a huge one. If you Google it, you'll simply find it. And the architects who built this one in that time didn't have any sort of finite element analysis tools, because it was not in place at that time. They just constructed it based on their experience, their feelings, their engineering judgments, etc. After a couple of 100 years now, they started to repair it, to add some elements, etc. Not add, but repair it mostly. They decided to do a comprehensive finite element analysis for this structure, because it's a very deep one, with very specific shape, with different elements. It's really complicated. They made a very comprehensive finite element model with some sophisticated softwares. And surprisingly, they saw that it's a very good design for the applied loads. Although there was not any sort of finite element analysis methods in that time for those engineers and architectures. So it means that even without any tools that today we have, they did a really good job in that time. And it means that besides any technical tool you have, like finite element softwares, etc., you should have engineering judgments as your first judgment in place when you design something. You should have some kind of sense with the outputs of your design when you design something. You cannot put just numbers into some formulas and get some numbers and say, okay, this is design. This is not how it works, how it should work. You should have some feelings based on which, of course, the more design thing you do, the more experience you get, the better judgment you will have. And this is why the design process is a lifetime process, as there is no end to it. So when you graduate, it's just the start, and you will learn, you should learn every day, day by day. And after probably 30 years of the design, you cannot say you have reached an end. You're just in the beginning again. It's a lifetime process. It's a lifetime learning. It's a lifetime adventure to learn better, deeper, and to be able to design more sophisticated projects and structures. That's it for today. And is there any question? Otherwise, have a good rest of the day.